Thank you for coming despite the terrible weather. Great weather. In some sense, it is great weather because when it's sunny and warm, you want to be outside. But in this weather, I certainly don't want to be outside. So it's a perfect time to find absolute maximum and minimum of functions. So why don't we do that? I would like to pick up where I left off last time and discuss the example of finding maximum and minimum of a function on a two-dimensional domain, which is a square. And I think it's a good example to illustrate the domain points and also to make a transition to the next topic which we'll discuss today, which is Lagrange multipliers. Okay? So we have a function. We have this function, and we have this the domain which I drew last time. It is a square. It is a square which is of a length. Each side is of length 2, which is situated on the plane like this. Okay, so we need to find the absolute maximum and minimum of this function. And the way I explain this is you have to follow an algorithm. The easiest way to solve this problem is to follow an algorithm. And the first step of this algorithm is to look at the interior of the domain. Okay. Should I do this example or not? Okay, thanks. All right. I think I should. I mean, I'll go quickly. I know that this was in last week's homework and stuff, and even quiz, I suppose. But since I started doing it, I just wanted to go quickly over it again. Okay. So step one is to look at the interior of the domain and to calculate the partial derivatives. And set the partial equal to 0. Okay, I'm going to skip that. I already did it last time. But this is inside the domain. So the next step, so that's very easy, right? So you just get two equations and you solve them. You find all the functions, all the points which satisfy these equations. And this will be the first points on your list. Next, you look at each component of the boundary. And on each component of the boundary, you can set one of the variables equals something. So effectively, your function restricted to that component becomes a function of one variable. So let's say if we take the part of the boundary which is that top horizontal segment, that would be y equal 1 and x between -1 and 1. When you set y equal 1 in the function, you effectively get a new function, let's call it g of x, which is x squared plus 1 plus x squared plus 4, which is 2x squared plus 5, right? 2x squared plus 5. And what you want to do now is to find the points where f g prime of x is equal to 0. So this will be the points on the boundary which are suspicious, which are candidates for points of maximum and minimum, right? And I purposefully just look at the interior, on the interior of this interval. So that means x is between -1 and 1, but strict inequalities. I didn't make this clear, I think, at the end of my last lecture, what exactly I wanted you to do at this step. And so I want to emphasize that what I was talking about is just finding the points where the derivative vanishes. And then step 3 would be just to include the corners. Now, there is a different way to think about this. There's a different way to think about this process. The way it's described in the book is there are two steps. Okay? First step is exactly the same as what I explained. But the second step would be to try to find the maximum and minimum of the function on each of the components of the boundary. Or, I mean, this is on the entire boundary, but effectively you will have to split it into 4 parts, right, and do it on each part separately. Now, what would be involved in doing that? It would. So let's say when you look at this, at my component y equals 1. When you look at y equals 1, you effectively get a one-dimensional problem where you have the interval from -1 to 1. And you want to find the absolute maximum and minima of the function g of x equals 2x squared plus 5. Right? So you split this problem into 2 parts as well. You look at the interior of the interval and you find points where the derivative is 0. Right? And also you look at the endpoints. So you have to look at the endpoints as part of the problem of finding the maximum and minima on this interval. Right? So what I did in my presentation of this algorithm, I have taken the endpoints and put them in a separate list, or separate sublist. So that in step 2, you would only be doing part of the problem of finding the absolute maximum and minimum on this interval, namely the points where the derivative vanishes in the interior. And then you have to deal with the corners being the endpoints of those intervals anyway. The reason I like this way of thinking about it is the following: that the same corner, say this one, will appear twice as the boundary of this horizontal segment and the boundary of this vertical segment. So if you go by the book, so to speak, right? So if you actually literally solve the problem for each of the segments, you have to include this point twice. Whereas what I'm suggesting, it's really a minor variation, right? But what I'm suggesting is that don't worry about the corners from the beginning. Just put them at the end. Include them. When I say include, I mean include them in your list. In your list of suspicious, maybe let's not use the word suspicious. Let's use the word candidates. Candidates for maxima and minima, right? So you include them anyway. So let's in step 2 then I'm suggesting not to worry about the corners, which could also be thought of as the endpoints of the one-dimensional problems which you get on the boundary, but instead just focus on the interiors of the boundary components and just find the points in there where the derivative is 0. Okay, so I think it's a slightly easier way to think about it. But if you like, it's okay. You can do it in 2 steps, so to speak. In other words, including the calculation of the corners in step 2. You just have to do the same work twice. I mean, you have to deal with the same point twice in this example. You see what I mean? Is that clear? So that's what I meant. I didn't really spell it out in detail. That's what I meant at the end of my last lecture when I said there's 3 steps. I don't mean by step 2 doing the entire problem of finding the maximum and minimum on each interval. I mean just doing part of that, namely finding the points where the derivative is 0. And then the endpoints you do as a separate step. So in this particular example, you have a list of how many points? You have quite a few. I mean, I'm not sure I should actually write them down, but you'll have some points which will have some points where the partial derivatives will vanish in the interior. There will be some points in the interior of those segments where the derivative vanishes. And finally, there will be the corners. So I have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I think I have 11 points. But anyway, it's not 100. It's going to be a small number of points. And then what you do is you just evaluate your function at those points, and you find for which points you get the maximum value and for which points you get the minimum value. It's possible there would be more than one point at which the function will attain the same maximal value. You just include both of them and say that the function takes the maximal value at those 2 points or 3 points or whatever. Okay? Any questions about this? All right. So the reason why this problem was relatively easy was the following. Step 1 would be essentially the same for all domains. I mean, for step 1, no matter what your domain is, you'll just have to calculate the points. You'll just have to find points where the two partial derivatives vanish, and then you have to make sure that that point belongs to your domain. So even if the domain has a complicated shape, right, that's not going to be so hard. I mean, you just have to know which points belong to this domain, which points don't. The problem would arise at step 2 if the domain is not quite so simple, right? So let me give you an example. So another example is a domain where x and y are such that x squared plus 4y squared is less than or equal to 1. Okay. So let's sketch this domain. So these are going to, first of all, when you sketch domains, by the way, this is a general rule which you probably have figured out already a long time ago. You have an inequality. You first look at the corresponding equality, right? So in this case, you will have just x squared plus 4y squared equals 1. And you sketch that, right? And that we know that's an ellipse. We talked about ellipses. So for instance, we have the point x equals 1, x equals negative 1, and y equals 0. And we also have the points y equals 1/2 and y equals negative 1/2. Two other points. And then the ellipse looks like this. Right? So it's kind of a circle which is squished like this. So that's the equality gives you a curve. And in fact, we can recognize our old friend, the level curve here. Right? This is the level curve for the function x squared plus 4y squared. But if instead of equality you write inequality like this, it means that in addition you include points for which the value is not equal to strictly 1 but could be less than 1. And that means that these points are going to be on one or the other side of this curve. In this case, it's easy to figure out which side. Well, first of all, they're going to be on the same side. And clearly x equals 0 and y equals 0 satisfy this inequality, right? This formula. And that's this point. So clearly it should be inside and not outside. That's how you figure out whether it's inside or outside, interior part or the exterior part of the plane. Or inside the curve or outside the curve. In this case, it's inside. And usually it's, it's easy to figure this out. So that's the domain. That's what now plays the role of this square. Okay? And let's suppose you're asked to find maxima and minima of the following function. I'll make the function a little bit easier, linear function, 2x plus y. So how would you solve this problem? Well, you approach it in exactly the same way. Solve it in the same way. Meaning that the first step would be to set fx equals 0 and fy equals 0, and find all the points inside the domain T, which satisfy these two formulas. So in this case, it's very easy to see that there are no points like this, because in this case, f sub x is equal to 2, so 2 equals 0, no solutions, and fy equals 0, also no solutions. Right. So in step 1, we don't get any contribution to the list of candidates or list of suspicious points. So everything goes down to the boundary. And in fact, there is no step 3 here, because there are no corners. The boundary is smooth. Right? So we'd like to understand this entire boundary sort of in one shot. How can we do this? The idea in the previous analysis was to express the restriction of our function to the boundary, or maybe a component of the boundary, as a function of one variable. Once it becomes a function of one variable, we can solve the problem by just going back to the one variable calculus. Right? But in this case, it's not so clear, because, well, in the old problem, it was very easy. You just substitute y equal 1, and of course, it's obvious that the function then becomes a function of only one variable, namely x. But here, what should you substitute? Well, one way to deal with this would be, one possibility would be to express one of the two variables on the boundary in terms of the other. So you could write, for example, x equals square root of 1 minus 4y squared. But there's a problem. We have two solutions. There's plus minus 1 minus 4y squared. Right? So in fact, what we're doing is we're taking this very nice domain, and we are artificially cutting it here and here. And so we're breaking it into two parts. One would be where x is greater than 0, or greater than or equal to 0. And the other one would be where x is less than or equal to 0. Right? Once you do that, so you have two components. Let me erase this for now. Two components. One is x greater than or equal to 0, and the other one greater than or equal to 0. And the other one is less than or equal to 0. And then you can try to solve the problem on each component. Right? So you would have to, you would get the function, say, g of y, which is equal to 2 times square root of 1 minus 4y squared plus y. This is in the case when x is greater than or equal to 0. And a similar function with a negative sign when x is less than or equal to 0. And you have to find the points where g prime is of y is 0. So you see that it looks kind of nasty, right? Because the function is not so nice. And if you split such a beautiful ellipse into two parts, then you have to also deal with the endpoints. There are no corners the way they were corners there, because there they were actually non-smooth. They were singular, kind of points of singularity. Here they're actually smooth points, but we have sort of artificially made them singular, made them look like corners, because now they appear as the endpoints of the they appear as the endpoints of these two parts of the boundary, right? So it is possible to solve the problem in this way, but it's just not a very elegant solution. So it is natural to try to find a more elegant solution. And the more elegant solution, so then it will still be step 3. Actually, in this approach, there will still be step 3, which will correspond to points x equals 0 and y equals plus minus 1/2, a kind of fake corners. Right? So what I'm going to explain now is a more elegant solution, which is called Lagrange multipliers. It's a more elegant solution which is applicable to even more sophisticated functions. In this case, we're dealing with a fairly simple level curve, or with a level curve of a fairly simple function. And that's why we can actually get away with expressing one of the variables in terms of the other. But let's suppose you had, instead of this, you had something like x squared plus 4y squared plus xy plus, some plus y plus square root of x or something. So then try to express now y in terms of x, or x in terms of y. That would be very complicated, right? Let alone, even if you can, then you have to take derivatives and stuff like that. So that's very complicated. But it turns out that there is actually a much more straightforward and elegant method. And that's called Lagrange multipliers. And actually, I would like to explain this method first geometrically. So let me look again at this picture. This picture, the domain D consists of two parts again. It consists of the interior of the ellipse and the ellipse itself. But we have just seen that on the interior of the ellipse there are no interesting points for us. There are no candidates for maximum and minimum because our function is such that there are no points where both partial derivatives vanish. So actually we can forget about the interior. The problem boils down to understanding the maxima and minima of our function restricted to just the boundary. There is nothing interesting for us inside. So that's why I'm sort of erasing this, and I'm just focusing on the boundary. And now I would like to approach this problem geometrically. In other words, we have discussed several times level curves. And for example, we recognize this curve itself as a level curve of some function. I said many times that if you know the level curves of a given function, you can understand much better the shape of this function. Right? So let's see how it works in practice in this problem. The boundary is given by an equation, so the boundary is a level curve. That's a given. But you also have a function, so you have to separate the two things. You have, first of all, you have the equation, this is the equation of the boundary. But you also have a function. And so what we can do is we can also look at the level curves of this function. Right? Here we're looking at just one level curve. Why only one level curve? Because this is the equation. The equation is that this is equal to 1. So we're just looking at one level curve for this function f. For this function, which let's call it something else. Let's call it h. I don't want to use g because I already used g for this. So this is a function h. For the function h, there's only one level curve which shows up in this problem. We don't care about other level curves. But for the function f, we would like to find maximal and minimum values, maximal and minimal values, and we don't know yet where they are. So we should look at all level curves for that second function f. So what do these level curves look like? So the level curves for f of xy equal 2x plus y are given by equations 2x plus y equals k, where k is some number. So for instance, one possibility is, say, k is equal to 0, 2x plus y equals 0. Any questions? No? All right. 2x plus y equals 0. What is 2x plus y equals 0? It's the same as y equals, maybe it's easier if I write it like this, y equals minus 2x. That looks like this. That's a line which goes to 0 with a slope is negative 2, right? And then if you look at other lines like this, for example, for instance, 2x plus y equals 1. This is just y equals minus 2x plus 1. So that's going to be a line which is parallel to this one, but goes through the point 1. So it's actually, in this case, it's going to cut here at the point 1/2, right? So I should do it more precisely like this. And so on. Well, my lines are not perfect yet. My lines are not perfectly aligned, but I hope you see what I'm doing anyway. All right. And what about other level curves? Well, of course, all other level curves are going to be just parallel lines. I mean, we are so sophisticated now, we even understand equations of planes in 3 space. For sure, we understand equations of lines on the plane. This looks like a typical equation. Well, if we had a z, that would be a typical equation for a plane in 3 space. And because we don't have a z, it's even simpler. So instead of a plane in 3 space, we get a line in 2-dimensional space on the plane, where 2, 1 is a normal vector. So when you vary this number k, you're going to get a system of parallel lines with such normal vector. Right? So I've drawn 2 of them, but now I'll draw more. So here's another one. Yeah, I kind of messed it up. Let me do it again. So I really want to emphasize the fact that this is a system of parallel lines. Okay, let's see if I can do it better this time. So we got this, we got this, and we got this. Okay, and now I want to draw a master line, which is going to be this one. I keep hearing voices like as if there is some color commentary, sort of to my play-by-play. I don't mind, but I'm sure that your people sitting next to you probably mind it. Okay, so you have a system of lines like this. Okay, so I think it's more clear now. Okay, so let's say that this one goes through 0. What is special about each of these lines? What is special is that along each of these lines, the value of the function f is the same. That's the function which we want to maximize, minimize. So we'd like to find maximum, minimum values of that function. And now what this picture tells us, it tells us the lines of equal value for that function. So for instance, the function is going to be equal to 0 along this line, right? The function is going to be equal to, where's my master line? This is my master line. The function is going to be equal to 1 along this line. The function is going to be equal to, say, 1/2 along this line, maybe 3/4 along this line, 1/4 along this line, and so on, right? Whatever line you want, you can draw, and it's going to be one of these parallel lines. Okay, but these are the level curves for the function on the entire plane. But for now, we are interested in step 2, so we're looking, because step 1 did not produce anything.